Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Today I want to talk about one of the neatest tricks in all of pure mathematics, and that's the averaging trick. This is a trick that you can use to get a really good handle on invariants. And what we'll do is show how that's the case, and in particular we'll show you roughly how Hilbert proved his finite generation of invariants. Okay, to look at this averaging trick, I want to remind you of hopefully some basic trick that you would have seen before involving even functions. Okay, so to get an idea of this averaging trick, let's consider the following. Okay, suppose you want to construct an even function, which is a nice symmetrical sort of looking object, because the graph you can represent as something which is symmetrical about the y-axis. Okay, so what's one way to do that? So what you can do is you can start with any function f of x. Okay, so maybe this one like this. And this one here is not symmetric about the y-axis, so it's not an even function. But what we can do is use this to create a new even function. So how do we do that? Well, we want to make it symmetric about this axis. So what we'll do is we'll reflect this graph about the axis, and we'll get another graph of a different function. Okay, so that'll be this one here. Something like that. And of course, it's easy to say, this is the graph of what function? It's the graph of f of minus x. Okay, so now the combination of these two is symmetric. Okay, but of course we want the graph of one function. So one way to get that is that we can just add these two graphs, in the sense that we look at the graph of the sum of these two functions, f of x plus f of minus x. So of course this function here now is even. If you swap x to minus x, these two sum and swap, so you get the same sum. Okay, so this is an even function. Okay, so the sum of these two functions is even. What we'll do more generally is we'll divide this by 2, which of course is still an even function. Okay, so this is a wonderful way where you can start off with any function and generate an even function from this. And what's more, in fact, all even functions have this form. And how can you see this? Well, if you have an even function, okay, how do you know you can write it like this? Suppose the even function is f of x. Then if you put that in here, that even function, you get f of x plus, and f of minus x is just f of x. So you'll get here in the numerator 2f of x. When you divide that by 2, you get the original even function. So every even function has this form as well. And in that way, you can get your handle on every single even function. And what's really nice about this trick is that it generalizes very easily to a huge swathe of examples. And let me show you exactly what that setting is. Okay, so we'll start with G is a finite group, and it's going to act linearly on some vector space over K, V. Okay, now we unfortunately have to have some sort of restriction on the characteristic of this field. The characteristic of this field K cannot divide the order of the group, and we'll see in a moment why that's the case. But other than that, that's a fairly general sort of situation. Okay, so let's see how we generalize this trick here. Okay, and the key is what you do is you look at all the symmetric looking things, okay, and you take the sum. Okay, so let's suppose we have some element inside this v, little v, and we want to get a handle on the vg. Okay, vg, the fixed point set with respect to the action of this group. So all the vectors w inside v, such that g dot w equals w for all group elements little g inside big G. So what we're going to do is we're going to form something like that. Okay, so what we'll do is we look at this v, and we look at all the images under the action of the group elements. So it's all the g dot v's. So we look at all these g dot v's. We look at the sum over all little g inside big G. Okay, that's what we'll do. And that's a sum over the elements of the group, and we're going to take the average. Okay, so we'll divide this by the order of the group like that. Okay, so that looks a lot like this expression here. And I claim that this element here is inside Vg. So that's the first thing. So that's like saying here you get an even function, so here you get a symmetric looking object. Okay, and what's more, you get all of this object this way. Okay, so how do I want to express that? I want to express that in the following way. So you've got a map here, V. If you take this natural, okay, you land inside this fixed subspace. So this these invariants, so Vg, and that sits inside V. So this map here is actually a projection onto this subspace Vg. Okay, so you'll get the whole of this in this way. Okay, So it's a projection map into this. And not only that, well, this map from V to V, this is a G module, this is G module, this is G equivariant as well. Okay, so what you'll find is that the kernel is also a G module, and this expresses this V as a direct sum of Vg, this subspace here, and another G module, which is a G submodule, and that's the kernel. Okay, so it projects onto that. And that's a rather nice fact, because if you want to, for example, say, what's the dimension of this Vg? Well, one way to think of it is, well, you have a projection here onto this, so that means it's just the dimension of this, it's just the rank of this projection matrix, which is also just a trace of this if it's finite dimensional. And the last thing is a bit more of a subtle point. I don't want to get into too much details about this one here, but this now is a family of operations that you can that you have. Okay, so one for each G module V's, each representation of V. Okay, you've got this natural operator. Okay, so in particular, if you have two different representations of G, so V and W, and a G equivariant map between them, you can ask, well, what's the relationship between this natural operator on this V here and the natural operator on this W here? And in fact, they are compatible in the following sense, that this diagram here commutes. Okay, so you've got this map F from V to W, a G equivariant map here. You've got the natural, which projects onto the fixed set, so it projects onto Vg here, and this natural is a different natural which projects onto Wg here. And what it turns out is that if you restrict F to this Vg, you get a map from Vg to Wg, and moreover, this diagram commutes. So it doesn't matter whether you go this way, do the natural here and then across, or you go this way and then you do the map that way. Okay, so this is a wonderful little proposition, and it really gives you a good handle on this fixed set Vg, okay, these invariants here. Okay, so let's just go through a little bit of why it's true. I won't go through the whole proof. It's fairly straightforward, actually. But it's good to see how this works and how this is actually inside Vg. That's a generalization of the fact that this is an even function. So let's see how that works, okay? So to show that this is actually inside here, we just have to show that it's fixed by any element of the group. So we're going to pick an element h inside our group and look at h dot v natural and see whether it's still just v natural, okay? So we're looking at h dot this element here. And remember, how does h act on this, okay? So this is a linear action, so it means that we can let h act on each of these elements and take the average that way. Okay, so what is this? We can take the average, okay, of h dot all of these. And by associativity of the action, this is hg dot v. Okay, so let's have a look at this expression here. We want to say it's v natural. But what have we done, right? So basically here you're looking, what are you summing over? Okay, these are all the g dot v as g ranges over all the group. Now instead you're looking at all the hg dot v's, okay? But where g ranges over all the group. But as g ranges over all the group elements precisely once, hg ranges over all the group elements precisely once as well. So basically this term here is exactly the same as this sum here. You've just permuted the order in which you performed the sum, okay? So it's exactly the same sum. So that means that this here is the same as this sum, and then you have the same average here as well. So you in fact get v natural. Okay? So that tells you, since this h dot v natural equals v natural for every group element h, that means that it's inside the fixed set Vg. Okay? So that's really, really nice, okay, that you have this fact. Okay, so let's just prove a little bit more of this and see how this works, okay? So let's check that it is a projection onto Vg, okay? So how do you check that it's a projection onto Vg? That means that if you're already in Vg, when you project down to Vg, of course, it doesn't change, it's itself, okay? So suppose you have something that's already fixed by all of G, okay? So if it's fixed by all of G, you can apply this procedure to that V. What's g dot v? Well, this is fixed by g, so that means that this is just v here. So you're summing v several times. How many times? The order of the group times. Okay? And then you divide by the order group. So of course that means that this average here is just V itself, in the special case where V is fixed by G. So that's why this V equals V natural if V is already fixed by G, and that tells you that this natural is in fact a projection onto this subspace. Okay, so once we have a projection onto this Vg, we can get our hands on it. Okay, and I'll show you lots of examples of how that works. Okay, now I want to generalize the setup that we're looking at a little bit more and abstract what's going on here. Okay, so far we're looking at just finite groups, but of course there are lots of other interesting groups where we want to study invariant theory. Okay, and the type of setting that works best are what's called linearly reductive groups, and I want to work in the algebraic setting of affine algebraic groups. So let's start with G, an affine algebraic group. So what's that mean? Well, all it means is that we look at a Zariski closed subgroup of this group here, GLNC. Okay, so let me just make sure you all understand what that means. So GLNC, okay, that's the group of invertible n by n matrices with entries inside the complex numbers. Of course, this is given by some n by n matrix, so you can think of this as sitting inside C to the n by n. Okay, this is some affine space over the complex numbers. Okay, and this is just some open, Zariski open subset of that, and it's the Zariski open subset where the determinant is non-zero. Okay, so we can look at this as an affine variety, and this is an open subvariety of that, and then we can ask for a closed subgroup of this group here, so a Zariski closed subgroup of this one here, which also just means it's Zariski closed inside here. Okay, so let's look at some examples so you're clear about what can happen with these affine algebraic groups. Okay, so the first example here is SLNC, okay, the group of n by n matrices with determinant 1. Okay, so setting the determinant equal to 1, okay, the determinant is a polynomial function in the entries here. So you're setting the polynomial in the variables equal to 1, so of course it's solutions to some polynomial equation. It is Zariski closed. So this is an example of a Zariski closed subgroup of GLNC, and hence an affine algebraic group. Okay, let's look at another example. Let's look at n copies of C cross. Okay, n copies of C cross. Well, I claim that this is also an affine algebraic group. Okay, you can make it a closed subgroup of GLNC. Okay, how's that? Well, if you look at all the diagonal matrices inside here, of course, what you get is that's a commutative subgroup. Okay, and you can identify it with each of the entries on the diagonal, and there'll be any of them, and they all have to be non-zero, so they're inside C cross n. And in fact, that gives you a group isomorphism of this C cross to the n with the diagonal subgroup of this, okay, the set of diagonal matrices inside here. Of course, is the set of diagonal matrices inside here Zariski closed? Yes, all you need to do is you set all the off-diagonal elements equals to 0. So they're solutions to polynomial equations in the variables defining it. Okay, so this C cross to the n, that's also a very important affine algebraic group. So for the third example here, I want to mention that this is going to extend all the notions that we have over here. It also includes every finite group. Okay, so now, of course, you have to think about what n you use for this GLNC, so I claim it is a Zariski closed subgroup of GLNC. Now, being finite, any finite set of points inside affine space will be closed. So you just have to make sure that any group does indeed embed inside GLNC, and that's because any group has a faithful representation. Okay, so for example, you can look at the group algebra, and that gives you a faithful representation, the regular representation. So that gives you an embedding of that finite group into some GLNC, and since it's finite, it's a closed subgroup and hence an affine algebraic group. Okay, so let's come to the notion of a linearly reductive group. Okay, so we just basically want to abstract this nice situation here, okay, where we have, we can get our hands on invariants, so fixed point sets, using some projection operator. Okay, so we'll abstract these in our definition here. So firstly, if you're given a representation V of that group G, or affine algebraic group G, if you have a G equivariant projection from V onto Vg, rho, then we call that rho a Reynolds operator. Okay, so here's an example of a Reynolds operator. From V to this Vg, you take this natural. Okay. Now, let's look back at the group. So this is for each representation of G. Now, we said that group G is linearly reductive when you always have this trick, this Reynolds operator, working like you do in part proposition C, in other words. Okay, G is linearly reductive if for every finite dimensional representation of GV, it always has a Reynolds operator, a G equivariant projection from V to VG. And what's more, if you have two different ones, V and W, and a G equivariant map between them, okay, now you've got two Reynolds operators, so replace these with the appropriate Reynolds operators, then this commutes, okay? So when that happens, when you have the fact that these Reynolds operators are always compatible with the G equivariant maps in the sense that this commutative diagram always commutes, then we say this group is linearly reductive, and then we can use basically the results of this proposition. So what are some examples of linearly reductive groups? Well, of course, the way I set it up, the proposition tells us straight away that any finite group is going to be linearly reductive. But what about other examples? Examples which are infinite. Well, we have this wonderful result due to Val, which tells us lots more interesting examples of linearly reductive groups. And this theorem is called the Val Unitary Trick. Okay, so suppose you have some affine algebraic group G, and inside this algebraic group G, you have a subgroup K, which is compact in the Euclidean topology, but dense inside G in the Zariski topology. Okay, so if that happens, then in fact this G here is linearly reductive. Okay, so I want to just vaguely suggest why this is true. So the basic idea is that for finite groups, what do we use? We use this averaging trick. And the key point is that, well, this averaging trick actually extends quite easily to compact groups as well. So there's something called a Haar measure on a compact group, okay? And then what you can do is you can integrate for your averaging trick using this Haar measure. And so this averaging trick actually works on K. And then there's a way to say that this averaging trick, the Reynolds operator you get from that, actually lifts to all of G because this K happens to be Zariski dense inside G. Okay, so maybe if I just look at some particular examples, you can see a better idea of what groups this applies to and also how this works. Okay, so the first example of a linearly reductive group is this one here, C cross to the N. Okay. So I've drawn here the example where n equals 1. So this is just a non-zero complex number. So it's the complex plane minus this point 0. Okay. So this is a multiplicative group. You just multiply complex numbers. And inside here you have a group which is the complex numbers of modulus 1. Okay, so that's a subgroup. And as a subgroup, so I've called it S1 because it's a circle here. As a subgroup, it's compact in the Euclidean topology. So if, instead of using the Zariski topology, use the usual Euclidean topology inside C. Okay, this is of course compact. And being a compact group, you have this Haar measure. And in this case, the Haar measure is very easy to describe, okay? Because you basically have an angular variable going from 0 up to 2 pi. So you can just, let's call it theta, and you can just integrate with respect to theta. So just integrate with respect to d theta, in other words, okay? From 0 up to 2 pi. And that works. Okay, so this here, it's a compact group in the Euclidean topology, and inside this C cross, it's actually Zariski dense. Okay, so in the Euclidean topology, of course, it's not dense, but when you take the closure in the Zariski topology, which is a lot coarser, you will get all of C cross. And why is that the case? So remember, how do you get the closed subgroups inside C cross? Okay, so remember the Zariski closed sets correspond to zeros of polynomial functions. So here you're looking at polynomial functions of just one variable. So if you have a polynomial in one variable, you take zeros of that. It's either you've got the zero polynomial, so everything is a zero, or you have some polynomial which is a constant non-zero, so there are no zeros, or you have something of positive degree, so you have a finite number of zeros. Okay, so this set is infinite. Okay, it's not finite, so actually it's Zariski dense, and that means that if you try to use the averaging trick here by using integration over d theta, okay, that will give you some projection operator, which is a Reynolds operator, and that actually extends to a Reynolds operator for the C cross action as well. Okay, So here, more generally in C cross to the n, S1 to the n, this is a compact group, okay? It's an n-dimensional torus inside here. It's a compact group that sits inside here, and it's Zariski dense, and that tells you that this here is a linearly reductive group, okay? So we have a nice Reynolds operator for it. Okay, another good example is GLNC itself is also a linearly reductive group, okay? So that's harder to see why that's the case. So in this case, you have the following subgroup, U and C. Okay, this is the unitary group, and this is actually a compact group when you look in the Euclidean topology, and it's also dense in the Zariski topology inside this. So as a result, you can apply Val unitary trick to show that this is linearly reductive. And this is an example, since you're using the unitary group here, where we get, which shows you why the name is the Val unitary trick. Okay, it's because of this unitary group here. Okay, great. So we've got some examples of linearly reductive groups. Okay, now we can come to Hilbert's wonderful theorem on finite generation of invariants. And in this result, he really proves something that mathematicians were working very hard on in specific examples, and he proved it in great generality and in great abstraction. Okay, so this theorem is the following. Suppose G is some linearly reductive group, okay, and suppose it acts linearly on some finite dimensional vector space V over the complex numbers. Okay, so in that case here, it basically acts on this as a vector space, but also as a variety. So it acts on the coordinate ring C of V as well. Okay, G acts on that, and you can look at the invariants. Okay, the fixed point set with respect to G. Okay, this R, it's clearly seen to be some sort of algebra over C, but the point is it a finitely generated algebra? Okay, so this is a finite generation of the invariants, and the point is it's finitely generated. Okay, so I can now show you using the Reynolds operator how that works. Okay, so it's linearly reductive, so there is a Reynolds operator. Okay, there's a Reynolds operator on V, and also all the symmetric powers of V, so actually on the whole of the CV as well. Okay, so you have a Reynolds operator there. I want to denote it using the natural, like we did in the proposition. Okay, so we need a little lemma before we start. Okay, so suppose we've got a little r, which is an invariant, and p is any polynomial, okay, in this V. And suppose we want to know what is the Reynolds operator applied to r times p. Well, it turns out it's just r times the Reynolds operator acting on p. So remember, the Reynolds operator acting on r is just itself, because this is fixed by G. Okay, little r is inside. Invariance, which is fixed by G. And the reason why that's true actually involves that compatibility of the Reynolds operator with respect to G equivariant maps. Okay, so since r is actually an invariant, okay, you can check that when you multiply by r, little r, you get a map from, of course, C of V to C of V, rather. So let's just change that. You get a map from R to R, but you also get one from C of V to C of V. Like that. Okay, it's a map from here to here. And using the fact that it's fixed by the action of G, you can see that actually this is a G equivariant map. Okay. And that's because G acts by algebra automorphisms here. Okay. So that gives you the fact that this is G equivariant. And then compatibility with G equivariant maps means that it doesn't matter whether you apply this G equivariant map first, which is left multiplication by R, and then take the natural, the Reynolds operator, or you take that Reynolds operator first, P natural, and then apply the G equivariant map restricted, which is left multiplication by R. Okay, so these are the same. Okay, great. So let's prove the theorem now. We've got all the technology to prove this wonderful theorem, and we'll prove it in the same vein that Hilbert did, and it's really ingenious, his proof. Okay, so of course this R here, because G is acting on each of the graded pieces, it acts on the degree 1 graded piece V, and on each of the graded pieces, you'll find that R, this invariant ring, is also a graded subalgebra of this polynomial ring C of V. Okay, so what we can do, of course, the constants will be in this invariant ring. Okay, it's an algebra over C, so it will contain the degree 0 part C. We're going to throw away that degree 0 part and look at the positive degree part. So R plus, it's graded subalgebra, so it's the sum of all the Rn, direct sum of Rn for n greater than or equal to 0. But if you look at only the n greater than 0, that part, that's the positive part of R. Okay, So that's just some, in fact, it's an ideal inside this R. And what we're going to do, it's rather ingenious. We're going to look at R plus, this thing here, and we're going to multiply it by C of V, okay, and put it back here so that this is going to be an ideal inside C of V. So we're going to use the ideal theory of this polynomial ring and the fact that we know about ideals in this polynomial ring. Okay, so that was one of Hilbert's insights, to use this ideal. Okay, so what can you say about that? Well, this is an ideal inside here, and as an ideal, it's finitely generated. Okay, so you can pick finite generators in there, and since the elements are basically CV linear combinations of things inside R plus, okay, what you can do is you can pick those finite generators to actually be homogeneous elements R1 up to Rs inside R. Okay, that's because every element inside this ideal is a CV linear combination of homogeneous elements. Okay, so that's what we'll do here. Okay, so remember, to show this as finitely generated, we need to pull out some finite set of generators. And I claim that this set of elements, R1 up to Rs, they're the generating set for this as an algebra, C R1 up to Rs. So they generated this ideal as an ideal over this ring C of V, and I claim that they become algebra generators for this R as a result. Okay, so of course, the reason why this ideal has finite generating set is because of Hilbert's basis theorem. Okay, so any ideal inside the polynomial ring, I guess the polynomial ring here is the theorem, so any ideal is finitely generated. And that's Hilbert's basis theorem. And this was initially something which is proved by showing existence of finite generating set, but the proof was not constructed. Okay, so I just need to prove this claim, and that will prove Hilbert's theorem, okay? That R is the algebra generated by R1 up to Rs, okay? So this R is a graded subalgebra, so to say it's generated by these, you just have to express each element as some polynomial in these. And since it's graded, you just have to do each homogeneous element inside here, okay? So you can do it by induction on the degree of a homogeneous R inside Rd. Now, of course, if you start with d equals 0, right, you've got all the constants, so the degree 0 part is already in there, okay? We're only interested in the positive degree part because the degree 0 part is automatic. And that's part of the reason why you're allowed just to pick this bit here. Note that if you included the R0 inside here, okay, the R0 you have 1, so this ideal is the whole thing, it doesn't tell you any information. Okay, so you've picked this R inside here. Now this R, of course, lies inside this ideal. Okay, so it's we assume that D now is no longer 0, so it's positive. So it's now inside this ideal. In fact, it's inside R plus. But since it's inside this ideal, then it's generated by these elements. Generated, when I say generator, I mean as ideal generators. So that means that you can write this R as a linear combination of this R1 up to Rs, but it's a CV linear combination. So it's going to be R1 P1 plus all the way up to Rs PS, where these PIs are inside this polynomial ring. Okay, so of course you want to write this element R as a polynomial in these R1 up to Rs. And unfortunately, these P1 up to PS, they're not even inside R at the moment. Okay, so let's see how we do this. Okay, so now this is where the Reynolds operator comes in and performs a real magic trick here. Okay, so R here is going to be fixed. And remember, the Reynolds operator is a projection onto the fixed point set, okay? A projection onto the invariants. So R equals R natural, okay? So what is R natural? Well, this natural is a linear operator. So you just have to take the natural, the Reynolds operator of each of these summands. And what's the Reynolds operator on each of these summands? Well, that's where we use the lemma now, okay? So the lemma says that since one of the factors is already fixed by all of G, okay, the R's are all fixed by all of G, you just need to do that R1 times the Reynolds operator applied to the other term, P1 natural. Okay, so here you've got P1 natural, R1 P1 natural plus all the way up to Rs PS natural. Okay, so we want to say this is some sort of polynomial in the R1 up to Rs. Okay, so let's see what we have here. So here we've got R1, Now this is P1 natural, okay? So the point is that R1, these R's, they were chosen inside R plus, so they have positive degree. So P1 now has smaller degree than this D here, okay? And when we apply a natural, it has the same degree, okay? Because G acts on V and it acts on each graded component, okay? So this has the same degree. So now P1 natural is something that's inside R because you're projecting onto the invariance now, and it has the same degree as this P1, which is lower down. So by induction hypothesis, we've got something inside R, but homogeneous of lower degree. It is a polynomial in R1 up to Rs. And all we did to this polynomial in R1 up to Rs was we multiplied by R1 to give you a new polynomial in R1 up to Rs. And then when you sum up all these terms, you find that you do, by induction, get some polynomial in R1 up to Rs. So this element is indeed inside this ring here, okay? So of course, this here, these R1 up to Rs, they're invariant, so they're inside this R. So this is a subalgebra of this. And what we've shown is that every homogeneous R inside here is also a polynomial in these R1 up to Rs. So these are in fact equal. And so Hilbert's theorem holds. This ring of invariance is indeed finitely generated, in fact finitely generated by this R1 up to Rs. I hope you enjoyed this adventure in pure mathematics.